Okay, thank you. Okay, nice to see you again. Okay, in this talk, I like to discuss how to generate large anisotropies in the stochastic gravitational wave backgrounds through the decay domain walls and the cosmic strings. This talk mainly are based on our recent two works. Oh, sorry. Here is outline of my talk. First, I will make a brief introduction, then introduce the domain wall and the cosmic string. Then move to discuss the stochastic background from the decay domain walls, and then from the cosmic string case. Then after, then a very brief conclusion. The LIGO, okay, has already detected more than 100 events of gravitational waves. The source of the most of the all source of the gravitational waves are stereo binary system with the mass around the 10 solar mass to 100 solar mass. However, the gravitational wave spectrum is quite wide. From the wave parity starts from the edge of the universe to the 10,000s, the 10,000s. If you look at the wave frequency, then the frequencies from the 10 up to minus 16 to the 1,000 hertz. And currently, people are most interested in 4 bands. For example, in this region, okay, such kind of gravitational wave, as you know, produced during the inflation, the primordial gravitational wave. Here you have to use the CMB polarization to detect the gravitational waves. In the nanohertz, the sources like the supermassive black binary systems, and we have to use puzzle timing arrays. And you know, in China, we have the bigger equipment. It's called the FAST. The sensitivity of FAST is much higher than the currently other equipments. It says within 2 years, the sensitivity, the data collected could be beyond to others. So it's a very hope to finally, okay, detect the gravitational wave in the nanohertz. As you know, 2 years ago, nanogravity claimed to observe the common spectrum process, but the final result still is not yet confirmed. In the minor hertz, then we have to space-based interferometers. Then the LISA, as you know, the LISA is okay approved, and it is expected to launch a satellite around 2035. In China, we have the 2 projects. One is called Taiji, another is called Tianqin. Is also on the way. We hope to within 10 or 20 years we could launch the satellites. On the ground, at the moment, we have the second generator detectors. Then we also hope to have the third generation detectors. Roughly speaking, the gravitational wave source could be categorized to two categories. One is called the cosmological source. Another one is compact binary systems. From the cosmological source, we have, for example, during inflation, we have the primordial tensor perturbations, and also like the phase transition and so on. In the binary, compact binary systems, actually between these 2 systems, actually for the gravitational wave from the cosmological source, the signal is stochastic and the continuous and almost isotropic. On the other hand, the gravitational wave from compact binary system, we have clear waveform and the signal is transit. And the source could be from the from the point. It means the location could be clear in the universe. And as you know, CMB is now the most precise position to the universe. And for the CMB, we have the spectrum. There is very clear, the Planck strain. On the other hand, isotropics on the CMB, I mean the fluctuation, could provide us more information than the spectrums. As you from this, the right-hand figure, then we can, okay, distinguish different model to different models of inflations. Then the question is that, of course, so far we still do not observe the stochastic gravitation wave background. Here I show you the figure. This is the stochastic background from the cosmic stream. This is from the preheating of the universe. This is the stochastic gravitation wave background from the binary system. This figure is a pulse spectrum for the first order phase transition. This is from the domain walls, and this is from induced gravitation wave produced during the inflation. And also, we still did not yet observe the stochastic gravitation wave background. Then, next question is, what kind of if there exists as any isotropics in the stochastic gravitation wave background, then what kind of information we can get? To generate any isotropic in the stochastic gravitation wave background, there are two ways. One is from the source, for example, preheating, phase transition, cosmic stream, cosmic domain wall, cover perturbations, and mainly from the density perturbations of the gravitation wave source. On the other hand, any isotropy also could arise from the propagation of the gravitation wave. For example, such a wave effect, inter such a wave effect. If the gravity is not GR, for example, modified gravity, also you could have any isotropics in the gravitation wave. Mainly the perturbations of the gravitation wave or gravitation potential. What any isotropies can we detect? First, okay, we should consider larger scale. During the inflation, it means the first several E-bodies. Another should be the strong. So it should be much larger than the CMB temperature perturbations. So in this talk, I will discuss the spectators in the inflation. For such kind of light fields, the mass is less than the Hubble parameters during the inflation. In that case, the perturbations are freezing outside the Hubble horizon. It means the perturbation of the light fields is classical, is a constant. Then the anisotropic in the stochastic gravitation wave background could be expressed like this one. Here, delta phi is the perturbation of the light fields during inflation. And kappa, of course, is a coefficient which should be model dependent. So this kind, if the delta phi has a large anisotropies, then we can get the large anisotropics in the gravitation wave background. The idea like this one. As you know, the inflation now is the crucial ingredient of the modern standard model of cosmologies. during the inflation. During the inflation, if some perturbations go out the horizon, then the curvature perturbation tend to be the constant. When it comes in, re-enter the horizon, then it becomes the source of the instability. This is the seeds of the larger structures. During the inflation, the quantum fractions, okay, will produce CMB fluctuations, also larger scale structures. During the inflation, the scale factor, the universe expanding exponentially, almost behave like this one. And usually we use such kind of model to drive the inflation of the universe. Suppose we have the scalar fields from the rolling down the potential, then the universe gets accelerated. During the inflation, actually, there is the quantum kickers. The variation of the phi is proportional to the Hubble constant during the inflation of the 2 pi. This is just the quantum effectors. In this talk, this one, the quantum kickers play a crucial role. During the inflation, some topological defects will form. Suppose this is the potential of some scalar field. The first vacuum here, during the inflation, because the field is light, so the fluctuation of the fields is frozen outside the horizon. In that case, what we are interested in is a large scale perturbation. And after the inflation, then the scalar field will falling down some vacuum, phi plus, or another vacuum, phi minus. In that case, the symmetry is spontaneously broken. During this one, okay, the topological factor forms. Then after with the expansion of the universe, the topological will evolves. In this talk, okay, I mainly will mention the domain wall and the cosmic string, the two kinds of topological defects. So domain wall forms if some Z2 reflection symmetry is spontaneously broken. For example, let's consider potential like this one. Phi the real fields. Of course, this is the potential. As you can see, there is 2 vacuums. One is, okay, phi equal to -2, another is 2. This 2 vacuum, of course, is generated. If we consider infinity wall, then the scalar field has a profile like this one, phi z, and sigma tangent z over delta. Delta equal to this one. This is determined by the parameter in the potential. Here is a profile of the scalar fields. In this side, the scalar fields following this vacuum. In this side, following this vacuum. Between two vacuums, there is a non-trivial profile. This is topological defect is called the domain wall. Here, triangle is nothing but the thickness of the wall. And the dynamics of the perfect gas of domain wall can be, okay, described by the average exchange energy tensor. And this one takes the form of the perfect fluid. Here, L is average separation between the domain walls. V is the velocity, average velocity of domain wall. Gamma is the Lorentz factors. As you can see, then the energy momentum, energy density of domain wall equal to this one, gamma square over eta. Eta is nothing but the tension of the domain wall. L, as I mentioned, is the separation of the domain walls. And the pressure is given this one. So equation state of the domain walls is depend on the velocity of the domain walls. If velocity is 0, then equation of state is -2/3, and the energy density behave like the 1/r. R is the scale of the universe. And if the V goes to 1, is the right, then the equation state can to be the 1/3. Then the energy density is 1/r4. So here RT is energy, is the scale factor of the universe. T is the cosmic time. So if the universe is filled with the gas of the domain wall, one could expect that the velocity will be rapidly shift away. So from the light, speed of light goes to the 0. In that case, the cosmos walls should quickly dominate both the radiation and the matter energy density. This is the disaster for the universe. And now let's move to the cosmic strings. Cosmic strings forms once the U1 symmetry is spontaneously broken. For example, let's consider the Higgs model here. Phi here is the complex scalar fields. F mu is Maxwell fields. The string solution was first found by Nielsen and Orson. At a larger distance from the infinite string, suppose the string along the z direction, then the phi could be expressed in this way. And the Maxwell fields can be the solution like this one. At a larger distance from the string, the phi can be expressed in this formula, and the Maxwell fields along the theta direction is R1 and R2 are two constant. So of course, this is the approximation solution. And n is the Whiting number here. For the string, the energy stress energy tensor associated with a long, thin, and straight string is given by this one. Suppose the string is located the x is the origin of the coordinate, and x equal to 0, y equal to 0 along the z. Then the energy moment explains this way. Mu is nothing but the tension of the string. Then the geometry of the string actually locally is flat. Globally, actually, there is the defeat angle, around the circle theta. And due to this one, the defeat angle, the three striking effects of the cosmic strings. One is the double measures. Suppose there is an object, a star, behind of the string, then the observer will see double images. The angle of the two images can be expressed by this formula. L is the distance between the string to the object, and D is the distance between the string and the observer. Of course, here is the linear approximation. And also, we have discontinuous in the temperature of CMB, because just due to the defect angle. The delta T over T equal to 8 pi g mu. V is the velocity of the string. So from this formula, we can get the constraint for the tension from the CMB observations. Also, there is a very interesting another feature. It's called the string wicks. Some of the particle, when some particle move around the string, we get the wave velocity of a particle. The velocity equal to this one. The stress energy tensor of the string case can be calculated like this one. And mu is, as I mentioned, this is a tension. L is nothing but is the average separation among the strings. Vs is the velocity of the strings. So here is this is the velocity of strings. Omega is the equation of state for the string case. Rho s is energy density of the string case. RT is the cosmic effect of the universe. If the universe is filled with of the gas, string gas, then if the string velocity is vanished, then the omega equation state is turned to the minus 1/3. On the other hand, then the energy density behave like the 1/r². If the velocity is approached to the light, the speed light, then of course the string gas like the some gas is the equation state is 1/3. So the low velocity string should quickly come to the dominant energy density of the universe because they behave like this one. This is a matter. This is the dust. So if because the velocity of string will quickly goes to 0 due to the redshift. So in that case, the string will dominate the universe. However, the evolution of string is much more than the string case because due to the string there will be interaction. So string network will be formed. Evolution of string work is more complicated than the string model. First one, the intercommutation of the intersecting string segments, which lead to the continued chopping of the long strings into smaller loops. Second, the decay of the small loops through the emission of the gravitational waves. So this is a very important feature of the string. In that case, the string actually is safe in the universe evolution, not like the domain war. The evolution of the string network, here the intercommutation plays a crucial role. Long string can be cut up into smaller segments and or loops. As can be seen, the energy density associated with long slow strings only decays as R/1/r², as I mentioned in the previous slides. Whereas the energy density associated with the loops like the R/1/r3, this is a behavior like the mat or the dust. So numerical experiment with the string network shows that after the string network is produced, it rapidly approaches to a so-called scaling solution, where in the radiation-dominated universe, the energy density of the string behave like 30 μ/T². And this is the behavior, this is the same as the radiation energy density. The ratio keeps a constant during the evolution, is fully determined by the tension of the string. Most of energy density resides in the few infinite strengths per horizon volume, while the rest in a scaling invariant distribution of loops. You have like this one. Here, this quantity is the number density of the loops at time t, with energy E for Q E plus the dE. These loops extending from the nearer horizon size downwards and are produced by the chopping of long strings through self-intersection and intercommutations. The actual energy density in loops behave like this one. 1/T² is determined is proportional to the tension. In the same way as energy density in long strings, actually, is the ratio of the string produced the gravitational wave relative to the radiation behave like this one. And Rho R is the energy density of radiation. Rho GW is energy density of the gravitational wave produced from the string. And gamma GW is a constant, something like the 20. And the T form is the time of the string network forms. Here where Ti is the time where loops first begin decay. The scaling solution depends on both intercommutation and the loop evaporation into the gravitational waves. Otherwise, the string would have the distrusted cosmological consequence. Now they are safe and have several potential interesting consequences. Firstly, is live with the background radical gravitation wave, because due to the oscillation of the gravitation wave, oscillation of the string, then gravitation wave produced. Secondly, lead to the temperature fluctuation in CMB, as I mentioned in the previous slides. And also the gravitation string, the string act as the gravitational lens. The first one is serve as a seed to the initial structure formation due to the weak velocity. Now let's discuss what we studied, the stochastic gravitation wave background from the domain wall. You know, one of the most important stochastic gravitation wave is the primordial gravitation wave caused by vacuum fluctuation of tensor perturbation during the inflation. The R is the ratio of tensor perturbation over the scalar perturbation. Currently, the constraint is less than the 0.06, even more less than this one. This is the power spectrum of the tensor perturbation. So once the primordial gravitation wave is observed, then we can determine the energy scale of the inflation, because the Hubble constant could be determined. In that case, the energy scale can be the potential of the scalar fields can be determined. Currently, the biggest problem, although we have a lot of inflation models, but we still know what drives the inflation of the universe and when happens. And currently, the CMB only can give the constraint for the largest scales. The perturbation in the small scale, we also we have no any idea about the perturbation at the small scales. The third one, if the Planck censorship conjecture is varied, in that case, the ratio tensor perturbation over the scalar period will be quite small. In that case, the primordial gravitation wave almost impossible to be detected. The anisotropies could be generated by various sources and the propagation process, but it's found that the anisotropies in most cases are challenging to be observed. There are many ways to produce the anisotropies, but the most cases, the anisotropies is too small. We explore the stochastic gravitation wave background produced from the cosmic domain walls and propose novel mechanisms to generate larger anisotropies in the stochastic gravitation wave background, which encoding the information of inflation. So it's helpful to determine the energy scale of inflation. The stable, as I mentioned before, the stable domain wall will finally dominate the universe. So we have to consider a model where one of the vacuum is slightly lifted so that the domain wall will annihilate before becomes the domination. Such a model can be realized in many models. For example, in the Higgs field models, X models, and some of the supersymmetric models. Here we consider the model like this one. The potential behave like this one. Before the two vacuum are generated, but now we lift one vacuum with some bias delta V. The formation of the domain wall is caused by quantum fluctuation of the light fields during inflation. This field is a lighter one, not driving the expansion of the universe, is not inflated. Here, the effect mass of the light fields is smaller than the Hubble parameter. In that case, the perturbations of the light fields remains constant on the super horizon scale. This is very important. After the inflation, because the Hubble constant decreases with time, and once H becomes smaller than the effective mass of the light fields, in the different regions, the scalar fields set down different vacuum, and then domain wall forms. Because in some regions, the scalar fields maybe here, then will get falling down in this vacuum. If scalar fields in some regions, scalar fields located in this region, then will fall in this vacuum. In that case, domain wall forms. This is a domain wall simulation. And as you know, the average radius of domain wall, of course, is the inverse Hubble horizon, Hubble constant, because this is, and the energy density of the domain wall is sigma, of course, is the tension of domain wall times the area of domain wall over the volume. Then A is constant, sigma is tension, this T is cosmic time. As you know, this one, of course, will dominate the universe. It's with cosmic problem. So now we lift this vacuum so that the true vacuum and vacuum, except the tension of the domain wall, there is a difference between the vacuum energy, so that the domain wall will be collapsed at some time at the T annihilation. This happens when the domain wall, the tension over the H, 1 over H, almost equal to the bias, then the domain wall will collapse, then will disappear. During the collapse, because there was generate inhomogeneity of energy density. In this way, the gravitational wave will be produced. Larger scale perturbations of the scalar fields remains constant at the super horizon scales, then will result in larger scale perturbations of the energy density of the domain walls, so that produce any isotropic in the stochastic gravitational wave backgrounds. This is a physical process. We find stronger anisotropies, at least at the 1 over 10, this order at the CMB scale is a larger scale, which could be used as a novel probe to inflation, because such kind of a larger anisotropy could be detected in the near future. Let's consider if the delta V bias term is this one, then the domain wall annihilate time like this one. A is a constant, something like the 0.8 is fixed by numerical simulation. Sigma here, once again, is the tension of the domain wall. As can be expected, the whole annihilation process of domain wall can be approximately treated as happens at around the annihilations time, T and this one. And most energy in gravitational waves is produced around the annihilations time. And the energy spectrum of the gravitational wave can be expressed in this formula. Here, epsilon GW tilde epsilon GW is the constant, something like 0.7. This is a numeric simulation result. And this one scale as K up to cubic for when the K here is the wave number. When the K less than the K peaks, then behave like this one. And beyond the peak, then the energy spectrum behavior 1 over K, like this one. So it's the spectrum of the gravitational wave from the domain wall is very simple. Here is the different parameters with the different colors. Sorry. This is one is for the tension, the time, and this is another one. And when the tension increases, then the frequency turn to be large. Here is a different sensitive for the different the detectors of. During inflation, Hubble parameter is almost constant. So E40 number can be expressed this one without the generality, lose the generality. Say the initial value of scalar fields in the region larger than that. Then the probability of the tilde phi at T is, there is one page missed. How to produce generate anisotropies? Quantum fluctuation of scalar field during inflation lead to perturbation at the super horizon scales. So initial background value of scalar field be set to be at this phi I at Ti. Then this is a probability when at this time T, the phi tilde is the spatial average value of scalar fields inside the one Hubble volume. This one is the solution of the what happens? P actually is just the solution of the Fokker-Planck equation. Then the probability of the phi tilde less than 0, then let's consider, because we have the two regions, one is larger than 0, another region is less than 0. In the less than 0 region, the probability is this quantity, integrate from the minus infinity to 0, then it can be given in terms of the area functions. Since phi remains constant at the super horizon scales, for any scale that leave and re-enter the horizon at T in the inflation phase and T prime in the radiation dominant area, the probability remains the same. This is, thus we can relate the probability T prime, this is the probability at the radiation dominated area, to the probability PT with the same modes. We can define this parameter alpha T equal to this one. Then largest scale perturbation of the light fields result in largest scale perturbation of the probability. This probability can be just this is if the phi has the perturbation, then the probability will change in this way. Here we emphasize that along the X, we apply the spatial average at a scale much larger than the wavelengths of the gravitational waves, but much smaller than CMB horizon scales. The energy spectrum of gravitational waves is proportional to the energy density of the source. Here we mainly consider at the time, around the time, annihilation of the domain wall. Then the average co-moving radius of domain wall at T annihilation is close to K peak. The K peak modes leave the Hubble horizon when during the inflation and the Hubble constant satisfies. This is currently the Hubble constant. This is the initial time during the inflation. So the E40 number for the peak is given this one. The alpha peak, alpha is the parameter I introduced in the previous slides, which is determined by the initial value of the scalar fields and the affordance before the end of the inflation. Then taking into consideration on the inability of the gravitational detectors to probe the high angular anisotropies of the stochastic gravitational background. So we focus on the larger scale anisotropies of the SGWB. Since for each K mode, anisotropies of this one proportion to the perturbation of the energy density of domain wall at T annihilation. So any anisotropies are independent of K. So then the perturbation can be expressed this one. The overline denotes the spatial average in total space. And the delta omega is proportional to the largest scale perturbation of the fields in the first order. If you explain this quantity, and the delta phi, of course, is the perturbation of the scalar fields. C1 is a coefficient, can be expressed in this formula. As such a plateau for CMB temperature fluctuation for small multiple L, the angular power spectrum can be expressed in terms of the power spectrum of the delta omega. The P, of course, the energy, this is the spectrum of the perturbation of the gravitational wave. So this formula is varied for small L less than 10. Then this must, so this one is independent of L. Because as I mentioned, during the inflation, the delta phi suffers from a quantum kick. Then this delta phi square should be equal to the 1 over h square over the 4 pi. In that case, this term can be calculated. If alpha peak larger than this one, this value, if the much less one, then one gets the n peak. N peak, of course, must be less than 6 as in the most inflation models. So L, this quantity L times L plus 1 times CL is larger than 1 over 100. So this is large enough. Setting phi I near the true vacuum of the potential, then phi I and nu are the same order. In this way, the inflation edge scale can be derived by this one. It means once determined, or once this quantity is determined, then we can determine the alpha peak. Then alpha peak is determined if the nu is fixed from some model, then we can know the energy scale of the inflation model. This is the new way to determine the energy scale of inflation model.
Okay, so 5 minutes left.
Okay, let's consider the model. For example, domain wall in the spontaneous breaking or discrete asymmetry in this paper. The tension, this one. The bias tension related to the mass of gravitational. Oh, sorry, there's and the energy scale, if we take this the initial value and the gravitational mass one is 1 mass, then the energy spectrum peaks at 1 Hertz with the peak value 10 minus 11, and the angle power spectrum equal to this one. This is big enough to be detected. Here I showed you the energy spectrum for the gravitational wave from the domain wall. This is the spectrum. This is the proportion to K cube. This is the K 1 over K. And this is the different sensitivities for the different detectors. So any anisotropic can be also be produced like the CMB fluctuations, but it's quite big. Another one, consider action model. This is the symmetry. Discrete symmetry is broken by the quadratic term due to this one. If we take the parameter like this one, the tension is this one, peak frequency is this one, and peak value of energy spectrum is this one, and the angle power spectrum for this one. This value can explain the common spectrum process observed the nanogravity 12 to 5 year. So If this is true, then such a large anisotropy could be observed in the near future. For the string case, of course, just from the Z2 symmetry is replaced by the U1 symmetry. If once the U1 symmetry is broken during the inflation, then string will be formed. The idea is that almost the same. Consider, for example, a gutter model, and phi is a complex scalar fields. We take the eta, the vacuum equal to this one, okay, during the inflation. The phi is a spectator during the inflation. Its quantum fluctuation, as I mentioned, quantum kicker, is larger than the classical value. Then we can neglect its classical motion so that the distribution of the phi can be described as the random walk around its initial value. This is just the solution of the Fokker-Planck equations. And the average length of this string region can be, okay, like explain this one. Suppose the initial value at this one, theta I equal to this one, then the length density of this super Hollow string taken into the expansion of the universe. Due to the universe, the number density of string loops with the length between L and L plus DL is this one. Here, okay, the length of string loops decreases with time due to the gravitational wave radiations. Gamma is a coefficient, something like due to equal to the 50 from the numerical simulation. And this can be calculated. We assume the cusp dominates the gravitational wave production from the string loops. Then the energy spectrum takes the form of the summation of the all harmonic loops of the modes of the string loops. Here, epsilon equal to this one is a normalizing factor. J denotes the J's harmonic modes. F is the frequency of the L is the length of the string, J is the modes, harmonic modes. So F is the frequency of the gravitational wave. The total one is explains this one. Here, the loop, this one, N is the loop distribution function, which is a number density of loops per unit length per unit volume. And take an example. Suppose the initial value at the force vacuum. Take the tension equal to this one. This is the energy spectrum. And as you can see, this one could naturally expand the common spectrum process detected by nanogravity. This one, this is nanogravity, the observation. This is a different sensitivity of the detectors. For the anisotropies, as you know, this can be calculated like this one. As a approximation, this is a proportion to the theta square. Theta square is defined this one. And the kappa, the coefficient, depend on the frequency. This is different from the domain walk case. And this figure, we show you the numerical result. As you can see, the linear approximation behavior is quite good with a different frequency. This is this different curve, the differences. This is the anisotropies of the gravitational wave. This is theta I. Theta I is the initial value of the spectrum or the scalar fields. The angular Paul spectrum at the largest scale can be expressed in terms of the Paul spectrum of the delta omega. Behave like this one. This one, of course, is varied, the small l. And this one also can be expressed, behave like this one, is a proportion to the frequency. Here, of course, we assume this one, phi I satisfies the Gaussian perturbation. That means the here. Sorry. Here, this one satisfies the Gaussian distribution. So we can get this one. And here, this figure shows you the dependence of this one depends on the frequency, this frequency, from nanohertz to the 10 hertz. This one for the nanohertz, this one equal to the in the order 1 over 100 almost, bigger enough. This is a PTA frequency. This is Lisa Taiji frequency band. This is Disigo, the BBO this band. This is a LIGO 1 with this one. So let's compare, make a comparison between the domain wall and the cosmic strings. First, of course, the symmetry is different matter. And the spectrum of the gravitation wave are also different. In the domain walls, this is a symmetry, Z2 symmetry, this is the U1 symmetry. In this way, there is the domain wall. For the domain wall case, we have the cosmic problem. But in this one, cosmic string, there are no cosmic problem. The parameters in the domain wall case, there are two parameters. One is the tension sigma, another is the time of annihilation of domain walls. For the string case, the mu tension and the alpha is the parameter I differ. The length of the ratio, length of string over the Hubble horizon. And any isotropic case, this is frequency independent. This is frequency dependent. So let me come to the conclusion. First, okay, the quantum fluctuation during inflation induces topological defects with a larger scale, stronger perturbations, which will produce the gravitational wave. And the corresponding anisotropic are detectable over the 1 over 100 in the scale. And anisotropic in the stochastic gravitational wave background provide the possibility to verify inflation and probe the inflation energy scale for the, especially for the low scale inflation model. Because for low scale inflation model, the pre-model gravitational wave almost impossible to detect. So in our work, we propose a new way to determine the energy scale of inflation through the anisotropic in the stochastic gravitational wave background. Okay, thank you.
Okay, so any questions? Oh. Okay, hi. I have a question. Usually cosmic string people consider this cosmic string formation at a much lower energy scale than cut scale. But it has not been found because of this constraint. I mean, gravitational wave constraint, the symmetry breaking scale is getting lower and lower, upper bound probably. But you are considering very high symmetry breaking scale formed, I mean, strings formed during the inflation.
Okay. First, okay. Here the energy scale is under the Gatt scale.
Yeah.
And as I show you, here the eta is energy scale.
It's also about 1/100th of the Gatt scale. 10
yes.
to the 10 to the 14.
Gatt scale is 10 up to 16.
Yeah,
GeV,
right.
Yeah. So here is this one is lower than the Gatt scale.
Yeah. But you are just a gravitational wave spectrometric strain. Stress must be consistent because cosmic strings are now diluted by the inflation. So energy density, cosmic string density must be much lower during the inflation. That's why it does not give much strain, stress for gravitational waves probably, even with that high symmetry breaking scale. But the problem is, the thing is, what about if such a cosmic string exists, that the deficit angle wouldn't change. So it has a huge deficit angle still.
Here's a tension, according to the current CMB constraint, the tension of gravitation wave. Oh, no. The tension of the string is get the constraint. G mu should less than the 10 up to -7 or something like that one.
Yeah.
Yes. And in our model, okay, as for example, to explain this, the nanogravity, the tension is, string tension is 10 up to -9. So it's consistent with the currently constraint. And the non-gravity, because you know, if there is also another explanation from the explanation for the non-gravity to the gravitation wave from the long string. In that case, the constraint is for the cosmic string, if my memory correct, is 10 up to 10. So in our case is one order higher than the long string. Here we consider the a sparse string network because the string actually is in the same scale as the hyperhorizon. So all the parameters, as far as I understand, okay, are consistent with the current constraint from the all
in terms
the
of this gravitational waves, right?
yes.
Yeah.
Not only the
But
gravitation wave, also from the CMB constraint.
okay, even CMB, but maybe deficit angle must be very different, right? Yeah, light
Currently
deflection.
for the string or the tension, of course, we'll get the more and more constraint, I think. But the such kind of small number of tension is still consistent. And the gravitation wave from the cosmic string is a very important gravitation wave source in the future gravitation wave detection.
Okay, so
for the PTA experiment.
okay, so due to the some tight time schedule, so we would like to thank the speaker Rong-Gen for his nice talk.
Okay, thank you.
Okay, thank you. Yeah. So